Hello, everyone, and welcome. We are excited to have you joining us today for the webinar. We will be getting started in just a few minutes to allow everyone time to join. In the meantime, please make sure your internet connection and audio are working properly. And just a reminder, this webinar will be recorded and available to watch on demand afterward. Before we dive in, let's quickly go over the interactive features of this platform. First, you can submit questions at any time during the presentation using the Q&A widget, which can be found in your console. Our experts will answer as many questions as possible during the Q&A session at the end. You can post comments using the survey link and also use live translated captions in your language of choice. A certificate of attendance will be issued from the certificate menu if you attend this webinar for more than 45 minutes. Please take a moment to familiarize yourself with the console. There are various widgets available, including resources, social sharing, and technical support. And if the slides are not moving as expected, please refresh your window by pressing F5. Now, let me introduce our speaker for today's presentation. We have Thomas Meyer, Senior Application Scientist at Oxford Instruments. Thomas is a Senior Application Scientist for Raman with a special focus on semiconductor material applications. He will be presenting on advancing full wafer and compound semiconductor research with Raman and photoluminescence imaging. We are incredibly fortunate to have his expertise to guide us through this important topic. Now it's over to you, Thomas.
Hello, welcome to today's webinar. The topic is Advancing Full Wafer and Compound Semiconductors Research with Raman and Photoluminescence Imaging. I'm Thomas Meyer. I'm a Senior Application Scientist from Oxford Instruments VTech. Before we start, I want to provide you a short outline of today's topics. First of all, I want to give you a little background information on confocal Raman imaging and PL imaging. Second will be full wafer imaging with characterization of stress and strain fields. The third part is epitaxy layer characterization. Then we continue with defect characterization, and finally we will have a brief look on full process devices. On the left side, you can see our semiconductors edition with a 300mm silicon wafer mounted. Let's get started with the background. First of all, I want to introduce our company to you. Then I want to explain the Raman effect, photoluminescence, and confocal microscopy. Last but not least, I want to introduce you to the semiconductor production cycle and where we can support industry and academia with our advanced metrology tools. Oxford Instruments is a large company containing different business units. So we provide atomic force microscopy, benchtop NMR, analytics for electron microscopy, 3D and correlative microscopes, which is covered by VTech, which will be our main topic today. So for the metrology part, I will focus on our 3D confocal Raman microscopes. Scientific cameras and spectrographs and cryostats are provided by Andor. Dilution, refrigeration and superconducting magnets are provided by Nanoscience. Etch and deposition processing equipment is provided by Plasma Technology. X-ray tubes are provided by X-ray Technology. With this large portfolio, we can support our customers in material characterization, life science, quantum technology, and of course, semiconductors. As our portfolio covers a wide range of material processing and characterization, we can benefit from synergies between the different business units. For example, there is a strong cooperation between plasma technology, which provides the material processing, and VTech for advanced metrology and material characterization. To support our customers, we have 28 offices in 18 countries with over 2,000 people globally employed. So there is a global distribution of technical centers, and we provide 24-hour service support with several support levels available. As you can see on the world map, we have offices on every continent. Let's talk about 3D confocal Raman imaging. To carry out high quality, high performance 3D Raman imaging, we wish for several things like a chemical and phase selectivity. We want a non-invasive and non-destructive method. It should be fast and of course confocal. And it should be applicable to individual types of samples, starting from chemistry over physics, biology, geology, and of course also the industry is addressed. And we want to cover several range sizes for the sample. So what is VTech providing to achieve these goals, to fulfill this wish list? So of course we need a high resolution in X, Y, and Z. We need a high sensitivity, a high speed, and of course to handle this data, which are pretty large, we need large data handling. So to fulfill all this, we need a trinity between resolution, speed, and sensitivity. Of course, all these 3 points should be carried out simultaneously. I want to introduce you the Raman effect. Therefore, we look at the simple molecule. In this case, it is methane. As Raman is based on inelastic light scattering, I want to explain to you what happens when light interacts with matter. When light interacts with a molecule, two things can happen. First of all, we can have elastic scattering. Here, the energy of the light is not shifted. This is the so-called Rayleigh scattering, which doesn't contain structural information of the molecule. This is what you see in the spectrum on the right side. The second effect what can occur is inelastic light scattering, as you can see on the left side on the molecule. So the scattered light has a slightly shifted energy, and this energy shift corresponds to vibrational modes of a molecule or phonons in a crystalline structure. To understand the Raman effect better, let's have a look at the Jablonski diagram. So on the very left, you see infrared absorption. For the elastic scattering, the Rayleigh scattering, and virtual energy state is excited, and as the electric state relaxes, the scattered photon has the same energy as the incoming photon. Next, we have a look at the Raman effect. Here, virtual state is excited as well, but when it relaxes, the molecule doesn't go back into its ground state as a molecular vibration was excited. And this energy difference can be measured. This is the so-called Stokes-Raman scattering. Here, the scattered light has less energy, so a higher wave number compared to the incident light. On the other side of the spectrum, you can see the so-called anti-Stokes side. Here, the scattered light has a higher energy, so a lower wave number than the incident light. This happens when the molecule is already in an excited state, so one vibrational mode is already excited, then the light interacts with the matter, the virtual energy state is excited, and then the relaxation goes back to the ground state. So, as said before, the energy of the light after the scattering process is higher than before. When we look at the molecule, we can observe different normal modes. For example, symmetrical stretching, asymmetrical stretching, scissoring or bending, rocking, wagging, and twisting. Of course, for semiconductors, the crystalline structures are more of interest. Therefore, we look for lattice vibrations, so-called phonons. These vibrational modes or phonons in crystalline structures correspond to the structural properties of the material, as the frequency of the vibration depends on the atoms involved. To provide you a better understanding, let's have a look at the characteristic Raman spectrum. In this case, as you see on the right side, we have a look at the spectrum of carbon C60. In the spectrum, you can see different peaks, and if you have a look at the different vibrational modes, one can nicely assign different vibrations to different peaks in the spectrum. So here we can learn about the nature of the chemical bondings. For example, we can discriminate a single, a double, or a triple bond in carbon-carbon bonds. Or we can learn about the associated atoms or molecules in a bond. We see the mode of the vibration, and therefore we can discriminate the crystalline structures and the molecule structures, as the spectra are always very material specific. Therefore, let's have a look how the chemical environment influences different peak parameters. Each molecule or crystalline structure exhibits its unique Raman spectrum. Therefore, the peak intensity can give you information about the quantity of a specific compound or the quantity of a specific atom bond within a crystal lattice, for example. The peak shift can provide you information about the stress and strain within the materials, which will be one of our main topics later. The peak width reveals information of the degree of crystallinity within the material, and of course polarization states also provide information about the orientation and the symmetry within the material. This of course has also an influence on the intensity of the peak. So now let me introduce to you the photoluminescence, or PL. As you see on the left side, you can see the band model of a semiconductor. Photon, an incoming photon, excites an electron from the valence band into the conductive band. Then internal relaxation processes take place and a photon is emitted. This emitted photon has a lower energy than the exciting photon. What we also discriminate is direct bandgap materials and indirect bandgap materials. For direct bandgap materials, the emission of the photon takes place initially. For indirect bandgap materials, the lifetime of the excited state is longer. The momentum of the excited electron has to change before it can go down into the valence band again. This requires an additional phonon. A typical direct bandgap material is, for example, gallium nitride. These direct bandgap materials are mostly used for light-emitting electronic devices like LEDs. Typical indirect bandgap material is silicon, which is mostly used for microchips, as everybody knows. Another representative of indirect bandgap materials is silicon carbide, which is used mainly for power devices. On the right side, we can see typical PL spectra of silicon carbide. So with the PL spectrum, one can discriminate the different polymorphs of silicon carbide, for example. Excitation energy for photoluminescence has always to be higher than the band gap. And the emission shows, of course, band gap properties and the energy of the band gap. Let's have a look on confocal microscopy. So why confocality is so important. Therefore, let's have a look at the detection beam path. When we have a look at the point of interest in the focal plane, everything goes smoothly and the light is able to pass to the detector. But what happens when we look at the point which is not the point of interest? So, for example, a point out of focus. Therefore, let's have a look at the beam path in this case as well. So here we marked a place which is not in the focal plane. And now let's have a look how the beam path goes through the system and what happens at the image plane in the back. If we construct the beam path from this out of focal plane point, one can see the image is created not at the image plane of the point of interest. And here comes the major part of a confocal microscope into the game, the pinhole. Because of the pinhole, all the light which originates from out of focus plane is not able to pass through to the detector. And thus we have a lot of benefits from this setup. So the pinhole in the image plane allows only rays from the focal plane to reach the detector. Thus, we don't have a global illumination, and with our setup, we don't have a line illumination as we do not use a slit, but fiber optics, which provides us additional benefits such as flexibility and a low footprint of the system. Once again, you can see the detection beam path. If we compare a classical to a confocal image, in this case of a cell, one can see a much smaller background and even substructures in the nucleus are visible. The introduction of the pinhole leads to real 3D information, which is not possible with a classical microscope. And additional, we have a slightly higher resolution in the XY plane. This, of course, is also beneficial for semiconductors. For example, when we have a look at the epitaxy layer, the 3D information can help us to distinguish between epi layer, buffer layer, and the substrate. And of course, the higher resolution in XY is also beneficial. Let's have a look into the manufacturing of semiconductors. So let's call it from ingot to microchip. Of course, this is a very brief overview and I will not go too much into the details because this would take a complete talk by itself. So basically we have ingot, in this case it's silicon, and then we have to undergo different processes to have the final devices at the end. So a part of the process or part of the steps are cutting, polishing, wet cleaning to get rid of the residuals. We need to do surface passivation or coating. Then the doping happens and photolithography, etching, chemical vapor deposition and epitaxy. And of course, these steps, they repeat itself as integrated circuits need to be created. On this slide, I will show you a bit more visual representation of the manufacturing process. So again, we start with the wafer ingot. The wafers are sliced, polished and cleaned. Then the wished pattern is transferred via photolithography. With this mask, we can create the structures of P and N doped materials by the usage of different dopants. Then the deposition happens by physical vapor deposition. Later, several structures are etched into the material, and then last but not least, the microchips are finalized and packed and shipped to the customer. The following slides will show you application examples from various steps throughout the manufacturing process. This will demonstrate where we can support customers from industry and academia in, for example, R&D, metrology, and quality control. The examples will cover full wafer imaging, epitaxy characterization, defect characterization, and fully processed devices. Let's talk about full wafer imaging. With the Semicon edition from VTech, we can investigate wafers up to a size of 300 millimeters, which are currently used mainly for silicon. I will show you two examples of 150 millimeter silicon carbide state-of-the-art wafers. The first application example shows you a high-resolution mapping of a 150 millimeter silicon carbide wafer. On the left, you see typical silicon carbide Raman spectra. For data evaluation, we concentrate on the E2 high band, which is stress and strain sensitive, and the A1LO/LOPC mode, which is doping sensitive. In the center, you can find the Raman image of the full wafer. The data evaluation was carried out with our true component analysis. So as you can see, the red spectrum corresponds to the red color in the image, and the blue spectrum corresponds to the blue color. As you can see, both spectra differ in the region of the A1 and LOPC mode, which is doping sensitive. Blue spectrum highlights the crystal facet with a higher doping concentration compared to the red one, which is the bulk material. As the wafer is always not perfectly plane, we always use our true surface technology to keep the distance between the objective and the sample always constant. This is important to measure always on the surface of the sample. This is very beneficial for the customer as you get the topography map, quote unquote, for free. With this information, you can calculate the bow and the warpage of the wafer. The next slide will show you a more sophisticated data evaluation of the E2 high band, which is stress and strain sensitive. Therefore, a peak fitting was done in every pixel of the 2D image. This slide shows you the peak position of the E2 high band and its full width half maximum. The peak position of the E2 high band is correlated to compressive and tensile stress. Peak positions with a higher wave number correlate to compressive stress, and peak positions with a lower wave number refer to tensile stress. As you can see in the image, in the center of the wafer, we have a more compressive stress compared to the edge of the wafer. The second image on the right shows you the full width half maximum of the E2 high peak, which is sensitive to the order of crystallinity. A narrow peak shows higher order of crystallinity compared to a broader one. As you can see, the distribution is almost homogeneous, except in the region where we saw the crystal facet. There a slightly wider peak is observed, and this can be explained by the different number of dopants, which cause slight changes in the crystal lattice. The second full wafer image reveals another picture. In this case, we don't see the crystal facet, but still we see two different phases. In this example, we can differentiate two polymorphs of silicon carbide. The red spectrum corresponds to the red color in the Raman image, shows you 4H silicon carbide with its typical peaks at 774 reverse centimeter and the A1 mode at 961.9 reverse centimeter. The blue spectrum refers to 3C silicon carbide, where we see additional peaks at 795.2 reverse centimeter and 969.8 reverse centimeters. Additionally, both spectra show a mercury line, which was used as an internal standard. As seen before, the topography of the wafer was recorded as well. As our true surface technology is a one-pass technology, we measure the topography simultaneously to the Raman measurement. So this doesn't require any additional time. One can see that the wafer from minimum to maximum has a height difference of 44 microns over the whole 150 millimeters. On this slide, I want to show you a 3D overlay of the Raman image and the topography. As you already assumed, the z-axis in this topography image is stretched. What one can also see is that the 3C silicon carbide is mainly located in the three spots in the center of the wafer and at the edge of the wafer. This slide contains a bit more sophisticated data evaluation. We will talk about the crystal polymorphs and their distribution and the peak position of the E2 high band, which is stress and strain related. First of all, I wanted to evaluate the distribution of the 3C silicon carbide versus the 4H silicon carbide. To quantify the area covered with 3C silicon carbide, the ratio of the E1 versus E2 bands was calculated. The E1 band correlates to 3C silicon carbide and the E2 band to 4H silicon carbide. As the E1 band is almost absent for 4H silicon carbide, the threshold was set to 0.1. So whenever the ratio was larger than 0.1, this pixel counts as 3C silicon carbide. With this threshold, I determined 133 pixels contain 3C silicon carbide out of 18,835 pixels for the full wafer. Following, we have an area coverage of 0.7% of 3C silicon carbide. This evaluation, of course, will give you the global view of the wafer. When we will talk about defect characterization, we will come back to this example and it will be discussed more in detail. As a second data evaluation step, the peak position of the E2 band was determined with peak fitting, again done in every pixel of the 2D Raman image, revealing the stress and strain distribution of the full wafer. As you can see, in the center of the wafer, we have again higher wave numbers, so more compressive stress compared to the edge of the center, which shows lower wave numbers or higher energy, which means tensile stress. To quantify this difference a bit more, I marked two regions in the wafer, as you can see in the histogram and picture below. The green area corresponds to the center and the blue area corresponds to the edge. And then the peak position of every pixel was extracted and shown in the histogram. One can clearly see that There is an overlay between center and edge, but nevertheless, one can nicely see a shift between center and edge. To calculate the stress and strain in megapascal, we used conversion factor from the literature, and then out of the 774.46 versus 774.483, one can calculate that there is a stress and strain difference of 7.43 megapascal from the edge to the center, and of course this is compressive stress. These were two examples of silicon carbide full wafer imaging. Both were recorded with 532 nanometer excitation wavelength. And I wanted to give you a short impression on what we can do with the data, what can we evaluate. And of course, this information helps the producer or academia to characterize the materials and to make them better in the end. The next important part in the quality assessment for silicon carbide wafers is the epitaxy layer. In this part, I will talk about the doping changes between the different layers and the layer thicknesses. In this example, I compared 3 differently processed wafers. This was done with Oxford Instruments plasma technology, which processed some of the wafer. So how were the wafers processed? The first one was prepared with chemical-mechanical polishing, plasma polishing tri-edge, and then the epitaxy layer was grown. The second one was only CMP plus epi, and the third one was only mechanically polished, plasma polished tri-edge, and then the epi layer was grown. For evaluation of the epi layer, the scanning direction was changed. The previous measurements were done in the XY plane, but here, as we want to measure in the depth of the wafer, XZ scan was chosen. This is possible because the 532 nanometer excitation wavelength light is able to penetrate into the material. So the material becomes transparent and we can distinguish different layers in different depths. So all 3 wafers showed the epi layer on top, which is marked red. Then we see a buffer layer, and then on the bottom we see the bulk material. The doping concentration for all 3 wafers is lowest in the epi layer, then in the buffer layer a bit higher, and then in the bulk material the doping is highest. How can we distinguish these doping levels? This is due to the A1 and LOPC mode. When we have undoped or nearly undoped material, the A1 band at 960 reverse centimeters is very narrow and high. But as the doping concentration increases, the peak position shifts to higher wave numbers. If the doping concentration is very high, an additional effect occurs. As we have more and more free charge carriers, there is also a plasmon resonance. And this leads to the curve, what you see in the blue spectrum, where the peak is shifted very wide to the lower energy range and the peak becomes broader. This is because this is now a coupled peak between the phonon and the plasmon. Here we were not only interested in the doping concentration, but also in the thickness of the epi layer. These results will be shown on the next slide. To determine the thickness of the epi layer, the intensity distributions for the epi layer for the 3 wafers were extracted. This you can see on the top left. To calculate the thickness, we have to take into account the refractive index as we measure the optical thickness with our microscope. With this method, we calculated the thickness of the epi layer was between 8.75 and 9.25 microns. These results go along with the information we received from the supplier, because they said the epi layer, including the buffer layer, is around 10 microns. We measured only the epi layer. The buffer layer can be measured independently, and the results will show that the buffer layer is around 1 micron in thickness. So this goes together very well with the information we received. The advantage of this method is, of course, you can measure the thickness afterwards, and as Raman is a non-destructive method, you don't destroy your sample. So you can nicely see what was happening through your growing process, and in the aftermath you can nicely evaluate the results. To characterize the wafers even further, so going on after the epi layer thickness determination, the doping concentration determination, the global view, we want to investigate now some defects. And therefore, of course, it's very important to know how they grew and how they impair the electric properties of the wafer. As you remember, we see the Raman image from the full wafer mapping, but now I wanted to go a bit more in detail, and therefore I used a bright field image from the marked area, and what we can see is this triangular structure. For evaluation, we now have two spectroscopical methods. One is Raman microscopy, which provides the structural information about the polytype of the material, about stress and strain, and about the doping. A second spectroscopical method is photoluminescence, which provides band gap properties and therefore the electric properties of the material. So let's have a look in these triangular defects. The first important question was, how is the shape of this defect even within the material? And here again we can use our 532 nanometer excitation wavelength, so we can look inside the material, as the material is transparent for this wavelength. A volume of 240 times 240 times 12 cubic microns was investigated within 1.5 hours. And as you can see in the spectra, one can discriminate three phases: the 4H silicon carbide, which is marked in red, the 3C silicon carbide, which is marked in blue, and the substrate, which is marked in green. The substrate shows again the higher doping concentration and therefore can be distinguished from the 4H silicon carbide. Of course, the substrate is also 4H silicon carbide. What we can learn from these images is how the defect propagates through the material and where it originates. Let's have a look at this more in detail. Gain understanding on the previously shown images, a 3D data reconstruction was carried out. The first animation shows all three components, so the 4H silicon carbide, C3 silicon carbide, and the substrate. The second animation shows only the 4H and 3C silicon carbide, and the last shows only the 3C silicon carbide. One can nicely see how the defect grows and propagates as the epi layer becomes thicker and thicker. So in this case, a carrot defect was there in the substrate, and then as the epi layer was grown on top, it grew wider and wider. The next question is how this affects the band gap properties. This will be shown in the next slide. This slide shows you a correlative Raman and PL measurement. On the very left, you can see the bright field image, and then on the top the Raman, and on the bottom the PL image. Raman spectra were recorded with 532 nanometer excitation wavelength, and PL spectra were recorded with 355 nanometer excitation wavelength. As for PL, the energy of the excitation have to be higher than the energy of the band gap. As one can nicely observe, the Raman image shows the two phases for 4H silicon carbide and 3C silicon carbide, marked by their characteristic spectra. The lower image, showing the PL results, exhibit more detailed picture. One can see three spectra which can be correlated with 4H silicon carbide, the red, the blue and the green one, and then two spectra which can be correlated to 3C silicon carbide, the cyan one and the orange one. For 4H silicon carbide, the band gap is observed at 391 nanometers, which corresponds to 3.17 electron volts. A second peak can be observed at 431 nanometers, which correlates with 2.88 electron volts. For 3C silicon carbide, the PL peak is located at around 530 nanometers, which correlates to approximately 2.3 electron volts. As one can imagine, it is crucial to have this information, as varying bandgap properties might impair the functionality of the power devices. This slide shows you the overlay of the video image and the PL image. As one can nicely see, the PL image reveals much more structure compared to the video image. On the right side, you can see four spectra obtained with spectral stitching over a very large spectral range, 355 nanometers up to 650 nanometers. So far, we investigated full wafers, epitaxy layers and defects. These three applications can be found more in the early stages of the production chain of semiconductors. Now, let's have a look at the fully processed device to see how we can help the industry and academia also on this end of the production chain. Here we can see a video image of a gallium arsenide-based microchip. In this case, the main task was to determine the depth of the trenches. Therefore, true surface was the ideal method to measure this. One can nicely observe how easy it was to measure the depth of the trenches. In this case, you see this 200 nanometers difference and compared to the noise level on a very flat region. A second task of this measurement was to look for contaminations on the contacts. In this case, we see the spectrum of gallium arsenide and no contaminations. A second area was investigated. Here, the investigated area was larger. It was 16,600 times 20 square microns. Raman and topography was recorded simultaneously as we do it usual. The Raman image shows the spectra for gallium arsenide and some fluorescence, which is decoded parts. The topography shows height differences of around 1.7 microns. In the lower right corner, you can see a nice overlay between the Raman image and the topography. For a detailed evaluation of the topography, a cross-section was computed. One can see the trenches are about 1 microns and 0.9 and 0.7 microns. The other parts of the microchip were very plain and flat as expected. To summarize these results, we had to look at the topography and contaminations on the contacts. Both measurements were obtained simultaneously, which saves time compared to two-pass technologies. Last but not least, let me summarize our today's webinar. At first, I gave you a little bit background of confocal Raman and PL microscopy. The second part of the talk was about full wafer imaging, where we investigated the stress and strain fields of the whole wafer. We had a look at the dopant concentration, and we identified areas with different silicon carbide polytypes. In the third part of this talk, we had a look at epi layers, so we compared 3 differently processed wafers in terms of the thickness of the epi layer and doping concentration. A large part of this talk was about defect characterization, so we investigated a triangular defect with Raman and with photoluminescence. We learned how this defect impaired the structural properties, so how it influences the polytype of the silicon carbide. Additionally, we learned how this defect had influence on the band gap properties. Finally, we had a look at fully processed devices. Here we looked for contaminations on the contacts and investigated the topography of the microchip. Last but not least, I want to thank you for your attention, and if you have questions, feel free to ask them now.
Thank you, Thomas, for the informative presentation. We will now begin the Q&A session. So on the call today, we have 3 Oxford Instruments application scientists from Japan, Korea, Taiwan, and also Southeast Asia, who will take turns to answer your questions. Then in order to manage our time effectively, we will address the pre-submitted questions first. And we may not be able to answer every question in the short period of time, but please be assured that we will follow up individually by email or schedule expert meetings with you to provide comprehensive answers to all inquiries. Okay, so let me check questions. Okay, so the first one is, I would like to know examples of how Raman spectroscopy being usefully applied in the semiconductor industry. For instance, describing real semiconductor materials where strand analysis is practically applied and indicating the levels of strand that can be measured. This is a very good one that touches on several applications of Raman. Let me take a look. Who can answer this? Kevin, can you take this one?
Sure. Hello, could you hear me?
Yep.
Okay. I think it's a good question. And basically, materials such as silicon, certified components, and silicon germanium can all be analyzed for stress using Raman. And the common application including like silicon wafer for the residual stress, maybe from ion implantation for doping, annealing, or CMP. And for those cases, the stress level will as low as maybe 50 millibar and it also can be detected. And for some epitaxy layer like silicon, germanium, and 3-5 material, Raman also can detect the strain due to the lattice mismatch during the heteroepitaxy. And for some process-induced strain like maybe some aging process or deposition process, Raman can detect localized stress in the range of maybe 100 to 500 megabar. And even for advanced packaging, maybe the structure like TSV, Raman also can help visualize stress distribution, especially like TSV and silicon interface. And the stress level in this case can reach about maybe 1 gigapart. So I think there are some examples from semiconductor field, but if your application isn't among the one I just mentioned, feel free to reach out to us. Yeah, this is my answer. Thank you.
Thank you, Kevin, for the answer. And we see another one coming in as the second question. So is it possible to identify small amounts, maybe less than 1% of impurities, such as antimony doping on germanium using Raman? Aki-san, can you answer this one?
Yeah, sure. So yeah, I would say, yeah, if the question means identify the elements, so such as antimony or other kinds of elements, yeah, it's impossible because our Raman analysis is not the elemental analysis. Yeah, it's a spectroscopy. And then if the okay, then how we can see the Raman peak. So for example, the germanium crystals, where we can detect the the Raman peak from the germanium crystals. But if the small amount of the impurity is included in these crystals, we can see only the peaks, the peak peak width is a little bit broadened, and then we can see very slight shift of the single Raman peak. Yeah, but the amount is, if the amount is too small, it's very hard to detect such of the small shifts of the small broaden the width of the peaks. Yeah, so I would say it's not easy. Yeah, and I would say, yeah, little bit difficult. Yeah, that's my answer.
Okay, thank you. Thank you. And then, oh, there are many questions. Let me take a look. Okay, so here's another one coming in regarding the depth profiling of dopants on a substrate. And I guess this means that what is the best method to set up and perform depth profiling of dopants on the substrate? Daniel, can you help on this one?
Hi, I will answer for this question. Actually, this question asking two kind of things. One is the depth profiling performance, and another one is dopants on a substrate. Actually, these two things are different. One, actually, for the dopant perspective, actually the dopant is, as the Aki said at the previous question, its UDEC concentration cannot be measured because the Raman is the qualitative analysis instrument. So actually, in case of dopants, it is rather than amount, but maybe you can get some carrier density change with the, you can see the carrier density change with the peak shift. So it is actually the usually can see the peak shift by the Raman. So any Raman can do this point. But in case of depth profiling, it is different, but changed by the wavelengths of the laser. I mean the excitation beam source. So as you know, it's if the wavelength is shortened, then the resolution becomes higher. So if you want the high resolution depth profiling, then you can choose short wavelength laser excitation beam source. So that is the answer. So and basically we say that the depth profiling, I mean the Z axis resolution is around 900 nanometer to 1 micron by the 532 nanometer laser. So you have to refer to this value. Thank you.
I also see some questions that are related to the system itself, so maybe we can answer these too. Like, okay, so something like, where is the mercury lamp located in the system? And can we simultaneously obtain the PL spectra and the Raman spectra at the same time? Daniel, can you continue on your support to this question?
Yes, I will answer about this. Yep. In case of HD ramp, usually it will be the argon HD ramp. It is located by from the outside or inside, both can be chosen. And actually, we need one of coupler to inlet the HD ramp right. So it is or that locate the I mean the coupler HD ramp coupler will be located on our optical microscope Raman tower parts. And next question was simultaneous or
yeah, can we simultaneously obtain the PL spectra and the Raman spectra?
Actually, PL and Raman spectra can be shown at one spectra, so you can check the simultaneously the PL and Raman together. But in case of Raman spectra, is very obvious because usually the Raman spectra is very low intensity phenomenon. So if usually the Raman spectrum peak is very slower, very lower than PL peak. So usually it is not shown when the PL and Raman coming together. But if the Raman spectrum and PL position is not overlap but near, and the Raman spectra showing very obvious, then you can see you can check simultaneously PL and Raman both. But it is actually unusual. So it is actually case by case. My answer is the case by case. Thank you.
Okay, and I can also see two questions from us from the same customer, which is the first one is, does 3D rendering require third-party software?
No, I don't think so. No.
Okay, so okay.
No, it's no. We integrate all the software function in the same software. Yeah, so you don't need any third party. Yeah.
Software. Okay.
Yes.
And was the wafer map round or squared? If squared, how did true surface work on the empty space outside the wafer?
It's a square mapping right now, and for true surface, because we can we can define the scan range. So the system avoid moving into the empty space. So it ensures stable tracking even at the edge.
Okay, and I think because of the short time period, I think we can take the last question from audience. So I think these two are quite related, so maybe we can answer this one. Like, can we use it to detect the strength in the scale of FinFET?
Yes. As I know, I already see some case for this 3D structure like FinFET or gate-all-around. Yeah, it's possible.
Okay, then I think we can elaborate more by scheduling an expert meeting with this customer. So, Mr. Zhang, we will be in touch soon to elaborate more and provide you more with the information after the webinar. Okay, and due to time constraint, I think it's time for us to wrap up the webinar now. And thank you everyone for your participation and engagement today. For those questions we were not able to answer in time, because I do see a lot of questions popping up in the inbox. Sorry for that, but we will definitely follow up shortly. And for any other support or further inquiries that you need, please scan the QR code on your screen to submit your request. Our experts are ready to help you with our solutions that can be tailored to your specific challenges and needs. So thank you again for your time. We hope you enjoy the time with us today and look forward to seeing you in future Oxford Instruments activities. Thank you.